Okay, so we want to continue our discussion with a continued discussion here on covalent bonding. So first, one thing we should talk about is if we think about two elements coming together, again, the electrons are on the outside, correct? And so when two elements come together, we have to recognize that initially there is some repulsion between these elements because they're electrons coming together towards electrons. Like initially there has to be some repulsion there of those electron clouds. But as they come together, as those two elements come together, what happens is the attraction of the nuclei to the other element's electrons is overcomes any electron repulsion, and what happens is they come together and bond, and that's when energy is released, and that is called the bond energy. The bond energy is the difference in energy between those elements being separated and those elements be bonded together. So when they come bonded together and that nuclei attracts the opposite electron, there is a certain amount of energy released, and there's energy released anytime we form a bond. As that attraction becomes more powerful, then it gets to that optimum length, which is its bond length, where they have an attraction between each other and energy is released. Now, if elements get too close together, then we get repulsion again, because then those nuclei get too close and they start repulsing each other. So there's an optimal length, which is called a bond length, where we have the most energy released, where we have an optimal attraction of nuclei to the opposite atom's electrons. Here's maybe a better diagram to look at, and this one's just with hydrogen. So again, we have the two elements. As they come together, there's some repulsion right here from the electron clouds, but then when they get past that special point, then the nuclei attracts the electrons, and energy is actually released when that bond forms. When this bond forms, energy is released, and notice its overall potential energy drops. So the energy of the system itself, of those two hydrogen atoms, drops. That makes it more stable, energetically more stable than if there's not a bond there. So it seems kind of funny that a negative state would be preferred, but it's negative for the element. It has lost electrons, it's lower in energy, and so it's more stable. And again, if it gets too close together, then there's repulsion of the nuclei, which again isn't favored. So there's this optimal bond length area where we can predict, where we also know the bond energy. So there's a correlation between the bond length, how close the nuclei is to the other nuclei, and the amount of energy that is released at that point. One other thing we might want to look at before we go on to drawing some of these compounds is there's also, we can see there's a correlation between the number of bonds. If we talk about single or double or triple bonds, their bond length. As we have more sharing of electrons, notice we have a shorter bond, and these are in picometers, so these are a billionth of a meter, so very, very small. But notice as that bond gets even smaller, notice we have an increase in energy. As we have more and more bonds, we can see the same pattern for nitrogen. The other thing that we can see is just tentatively shorter bonds have higher energies as well. So just shorter bonds tend to be higher in energy than longer bonds of the same types of elements. If we look at bonding within a group, so this is down our halogens, we have hydrogen bonded to iodine, bromine, chlorine, and fluorine. Notice this element is getting more and more electronegative. As our element gets more and more electronegative, notice our bond length gets shorter and shorter and shorter. And what we would also want to know is our bond actually gets stronger. So it gets shorter and it gets stronger. And the reason why in this case, down this one group, is because we have a more electronegative. So it's getting stronger because our nonmetal is more electronegative. So we're going to see some patterns between electronegativity of our nonmetal with the bond length and the bond strength. But let's do something a little bit more enjoyable. Let's actually draw some compounds. So to be able to draw the compounds, the first thing we need to do is be able to write the Lewis dot structures for the individual elements, which I believe we can do. That, again, is just going to be dependent upon what column they're in. Now, notice this has eliminated out our transition metals are just cut out of this because, again, most of our covalent bonding is happening with nonmetals, which, again, the more common ones are going to be within the first 2-3 energy levels. And so we have, this is group 1, again, alkaline metals, group 2, 3, 4, 5, 6, 7, and 8. So notice when we write them, we just put, for fluorine, for instance, It's in group 7, so it has 7 valence electrons. Again, outside electrons. And again, we're concerned about outside electrons because those are the ones that are going to interact with other elements. Now, if we want to see how these elements bond to themselves or each other, what we're going to do, if we want to predict, well, say how is carbon, with its 4 valence electrons, going to bond to a single molecule of oxygen that has 6? Well, we write down those elements with their valence electrons, and then we just start connecting them. So I'd say, well, they could share this one pair of electrons. Well, now, do they have an octet, either of them? Well, carbon, if I count it, has 1, 2, 3 electrons of its own, and a pair, that would be 5. So that is not an octet, so that cannot work. Also, oxygen, if we count up oxygen, is not happy either. It has 5 electrons of its own, and 2 that are shared for 7. So let's try this. Let's try sharing one more pair of electrons. So I'm going to do that. If I do that, now notice oxygen. Oxygen has 1, 2, 3, 4 electrons of its own, and then 2 bonds which each have 2 electrons. So oxygen has 8. Oxygen actually is happy. It has an octet. That's great. However, carbon doesn't. Carbon only has 2 of its own. So it has 2 of its own and 2, 4 that are shared. That's a total of 6. It does not have an octet. This is not a stable compound. But we can still figure it out. Let me erase it, though, so we don't get too much of a mess. And I'll move this guy out of the way. Okay, so start this over. We had 1 shared pair. We had 2 shared pairs. It wasn't happy. Well, then what's typically going to happen is we're going to share 3 shared pairs. But if we do that in this instance, maybe we'll try that. Try sharing this pair. Notice that doesn't make anybody happy. Because if we count up oxygen, it has 1, 2, 3 electrons of its own, and now 3 shared pairs for 6, so oxygen would have 9 valence electrons, and carbon here has 7, so that doesn't work either. But notice 7 and 9 were close, right? So let's try it one more time. So we shared 1 pair, we shared 2 pairs. We know there must be some trick, and this actually is the trick, that this lone pair actually gets donated and becomes the triple bond. Notice if we do that, if I write them with 1, 2, 3 bonds in the middle, and notice keep these 2 on carbon, and keep this and this one on oxygen, then notice both of them have the 3 shared pairs for 6 and a lone pair for 8 electrons. So that is a stable structure. So we can do that. So think of those valence electrons as being very, very mobile. They're going to move around so that everything has an octet in any way that they can. In this case, it actually donates one of its lone pairs to form that triple bond. That is actually called a dative bond. We don't see that a lot, but it is an option for you. So maybe we should actually start with some easier examples. So here's nitrogen. It's in the 5th row, so it has 5 valence electrons, so I make 5 dots around it. Fluorine, each has 7. Pretty clear that if we're trying to draw an F3, we can see that there's a bond here, and a bond here. So these all form single bonds. If I wrote it as a Lewis dot structure, I would write it like this. There's a bond. Let's see, this one has 7. There's a bond. And this one has 7. There's a bond. So all my fluorines are happy because they all have 6 lone pairs, and they have 1 shared pair. So that's a total of 8. Nitrogen is happy because it has, again, 3 shared pairs for 6, and its lone pair for 8. And the lone pairs are essential. So do not erase them or ignore them once you've built your structure. Here's some other examples, and I apologize that they're blurry here. They're actually not blurry. They're really just you. Are you wearing your glasses? Okay, but let's look at these examples. So here we have a Lewis dot structure of oxygen. It has 6 valence electrons. So this is the structure of water. How's water going to bond? Well, each hydrogen has 1. Oxygen has 6. If we share this pair and we share that pair, now oxygen has 1, 2, 3, 4 of its own, or 2 lone pairs. 2 lone pairs for 4 electrons, and has 2 shared pairs for another 4 electrons. So it has 8. And remember, hydrogen is happy not having 8. So hydrogen can be okay that way. And I would rewrite this structure like this. Oxygen in the middle, 2 lone pairs, and again, essential that we leave on the lone pairs, or we show that they exist. Here we have nitrogen again, and look at nitrogen still has 5 valence electrons. If we're trying to see how it bonds as an ammonium, well, this can be a pair, this can be a pair, this can be a pair. Look at that. Now, nitrogen again has 2, 4, 6 that are shared, 2, 4, 6 that are shared, and it's shared pairs. 1 lone pair, it has 8. So notice nitrogen is going to often form a structure that's similar to this. Now, if we look at the structure of methane, CH4, well, Carbon has 4 valence electrons, so we'd write carbon with this 4. Write the hydrogens around it. 1, 2, 3, 4. Notice carbon is using all of its electrons, which is very common for carbon in its bonding. So it has 4 shared pairs for a total of 8. Again, hydrogen's happy because each hydrogen has 2. Here's some more examples. How do we form CO2? So we looked at carbon monoxide. How does carbon dioxide form? Well, notice we can share a pair here, share a pair here. Now, how do I know carbon's in the middle? Well, carbon, because it has 4 valence electrons, is often in the middle. That is the easiest way for carbon to bond. Well, I shouldn't say easiest. That's probably not a good word to use in a science classroom. We often find carbon in the middle of structures. Or structures tend to be symmetrical. That's another way to think about it when we're laying out elements and they're Lewis structures. We're writing their Lewis structures to see how they bond. So it can share a pair on each side, but notice they're not happy. 1, 2, 3, 4, 5 on oxygen, plus a shared pair 7. Carbon has 1, 2, 3, 4 in its shared pairs, and 2 lone pairs, that's 6. And this oxygen also has 7, so that does not work. Well, we'll have to try something else. I'm going to leave those bonds. I'm going to try sharing one more pair over here. Now notice oxygen has 2 lone pairs, so 2 lone pairs, and 1, 2 shared pairs. That is a total of 8. If we do the same thing over here, that oxygen has 8. Now let's look at carbon. Carbon has 4 shared pairs for a total of 8. I would probably write that structure as a Lewis dot structure more like this, but then we can see how that is working. Now we have nitrogen. Each nitrogen has 5 valence electrons. Now let's start sharing pairs. Share 1 pair. Now each one has 6. Share another pair. Each one has 1, 2, 3, 4, 5, 6, 7. Share another pair. Each one has 1, 2, 3, 4, 5, 6, 7, 8. So that's how they bond. Each one has 1 lone pair, right? And 3 shared pairs. Now, one thing we want to be careful of here is we're looking at a triple bond. Our atoms very rarely form anything, they do not form anything further than a triple bond. There's really just not space for overlapping between those elements to form anything other than a triple bond. So we can form single bonds, we can share 2 pairs, have double bonds, we can share 3 pairs and have triple bonds, but we can't have more than that. Notice we can share things that aren't just simple molecules that get larger as well. Notice here is a structure called bromoethene. 2 carbons, 3 hydrogens, 1 bromine. Again, they put the carbons in the middle because that's typically what we do. Then they just started attaching everything. Attach those, attach a bond here, a bond there. So first I'm going to make sure everything's bonded once. Notice there was 1 extra pair of electrons left between those carbons, so they formed a double bond. So that's how we got from this over to here, which is how I'd rather draw it as opposed to having those electrons between. Same thing over here. We're going to form a bond between the hydrogen and carbon, between the carbons, between the carbon and the iodine. Now we have some extra electrons, and guess what? If we form them across the carbons, we get this iodoethene. And right now, we're not naming these compounds, we're just drawing them, so don't worry about the naming. You can also see the hydrogen cyanide here. Form a bond here, form a bond here. This one needs another, and another. That's how we're going to get our hydrogen cyanide. So far we've been following what's been called the Octet Rule, which says that atoms are most stable if they have a filled or empty outer layer of electrons. So this is true for our ionic or our covalent compounds. We've been working on covalent, sharing electrons to get up to 8 to get to this octet. And now what we'll tell you is that there's a few things that do not obey our Octet Rule. One we already know is hydrogen and helium. Because they're so small, they form what's called actually a duet. They want 2 electrons, not 8. But there's going to be some other exceptions we run into. Our 2 most common are beryllium and boron. Beryllium has 2 valence electrons. Boron has 3. So what happens to these is when they react with a very reactive halogen, that halogen, like chlorine, comes in and forms single bonds with the electrons that are available from boron before boron has a chance to form any double bonds or anything like that to maintain an octet. So boron will do this with chlorine. Boron will do this with fluorine, reactive halogens. We see this a lot with. But again, only with beryllium, boron, that's where we see it most often. There's a few other exceptions. This is phosphorus. Pentachloride is an exception. Again, phosphorus, notice how this forms. Phosphorus has 5 valence electrons. If chlorine comes in, or also fluorine, very reactive, grabs each of those, forms bonds. Notice that's how sulfur forms. Sulfur hexafluoride here. Sulfur has 6 valence electrons, comes in with a really reactive element like fluorine. Each one wants to form a single bond, each one wants an electron, and it reacts with them. Another thing we'll run in with when we're writing these Lewis dot structures is occasionally we'll run into a compound like this. Now this is O3, this is ozone, and how we write it is like this. That's how we maintain our octet. Now, sometimes people like to try to make a ring out of this, but it doesn't really form a ring. This is the structure we have. Now, notice you could write this a different way. We could erase this, and we could put that double bond over here, and we could put that lone pair, just like it shows in the structure, over here. Now, which one is correct? Which is the most accurate? Well, in reality, they're both entirely correct. And they both exist. These are called resonance structures. And if we want to accurately rewrite the compound, we have to show both of them. Because in reality, oxygen, or ozone in this case, doesn't have one double bond and one single bond. What it actually has is 2 bonds that are about a 1.5 character. So they're halfway between a double and a single bond as far as their bond strength goes. So both of these actually exist. And they'll switch back and forth in real time. So there's kind of an equal sharing going on between these. So there's neither a double bond nor a single bond. There's actually a 1.5 bond character. So what we'll see is we'll write both of these resonance structures is the proper way to describe that, where this electron pair will fall down, form the double bond, and we'll kick this one out onto that outside electron. So it now has 6 lone pairs of electrons. One more resonance example that's really, really common, and I'll finish it here, it's not completely correct, is sulfur trioxide. This is one you see a lot on tests and things, where the sulfur bonded to 3 oxygens in a very symmetrical structure, but there's one double bond somewhere. Well, that double bond can be in 3 different locations, actually. So what we have to write is, if we want to accurately write the structure, we have to show all 3 structures. And often what they want us to do is show that this bond moves around. This lone pair drops down, forms a double bond. That lone pair breaks. And then likewise, this one can fall down, form the double bond that side, and this one can break and shoot those electrons out there. So notice what we really have is sometimes they'll write the structure like this, or that one's actually kind of dirty. Well, not dirty in a bad way, just dirty. We'll write it like this with like a dotted line and one single bond, showing that it has something beyond a single bond, but not a full double bond. So it's kind of a dotted second line there to show there's resonance. And so again, this is our resonance structures. So sometimes people like to have rules about how to do things. So if we want rules about how to draw our Lewis structures, one thing that we can do, especially if we have a more complex structure, say we have something written out like this. We have acetic acid, so H3. Acetic acid here, so CH3, COOH, and we need to know the Lewis dot structure. Well, what we do is look up the elements, count their total number of valence electrons, draw a provisional skeletal structure, so that means you draw the elements out. You have the total number of electrons that are there. Now I'm going to put things around it, because the carbons are probably going to be in the middle. I'll start attaching them. There must be a bond there, bond there, bond there, bond there, bond there. Bond there, maybe a bond there, I don't know. We count the remaining electrons. So if we knew the total number of valence electrons here, carbon has 4, each hydrogen has 1, that's 3. This carbon has 4, each oxygen has 6, that hydrogen has 1, and we put those in. Now we can just add up that total number of valence electrons, which is 24 electrons, and we can see how many we use. 2, 4, 6, 8, 10, 12, 14. 14, so we have 10 more electrons to put in, and we'd have to put them in somewhere so that everything has an octet. So you distribute those electrons, check that everything has an octet. If it does, and it looks like a realistic structure, so this says check for common bonding patterns, but right now, starting out, you don't know what common bonding patterns are. So right now, I'll stop right here. Check for octets. Is everything have an octet? And then you're probably okay. You're probably done. If not, then try again. Take all the electrons off. Try new structures, see if we can find where those electrons go. I would notice if I tried doing it this way that this would really not solve our problem. But if I put that option in that hydrogen like this, now I bet you can find a place for those other 10 electrons to see how the structure is actually bonded.